Let's see. So our next speaker is John Donahue from Beaufort, South Carolina. He runs the crime lab there. And John is not unique, but a rare individual who thinks that the concept of what you want to do in a crime lab is use the best technology you can to get all the truth you can out of evidence. That's not the most common, right? So that's laudable. It's not common, and we'll hear more about how John does that in his lab, getting truth for justice out of science for the next half hour.
Right, so I want to apologize for the wordiness of this title. I was told to write something that was very descriptive of what I was going to talk about. In the laboratory, we kind of use this as jokingly refer to it as pompous verbosity, which being that you're lawyers, you're probably familiar with the concept. But basically, what I'm going to talk about is how we use computers to speed things up in our lab, to automate things, really, to speed it up, improve data recovery from samples that would previously have been called inconclusive or not suitable for statistical analysis. So you may be wondering where exactly Beaufort County is. It's all the way down there in the red in the bottom. Beaufort, Bluffton, Hilton Head Island. Believe it or not, there's more people out there, I think, from Ohio and Pennsylvania than there are from South Carolina. And just to dispel stereotypes, our lab's not in a trailer. We're in the deep south. We took the wheels off, so it's no longer mobile. But, a county of 185,000 people, which, raises the question, well, why do you have a lab in the first place? Well, the same reason that everybody else has a lab, right? Number one, to help identify perpetrators of the crimes that go on in our county. Number two, to eliminate the wrongfully accused. We don't want to be sending anybody to jail who's not supposed to be there. And number three, to help prevent future crimes. And this is kind of one of the things that I've gotten more interested in here in the last few years. Can we do things to help reduce future crimes? Does DNA testing help in that regard? So just something that was done a few years ago in Denver, Colorado. They did a pilot program, the DA's office. They used DNA testing there to investigate property crimes and to ask the question, what would happen, the crime rates here, what would there be a financial impact if we started going after property crime offenders? And so in their testing, they identified about 90 or so habitual burglars, people who had prior convictions, multiple prior convictions of burglaries, and then putting some formulas together and estimating costs of investigation and everything else, they came up with a rough estimate of about $37 million saved in property losses over the 2 years and about $5 million in police costs. So they figure it worked really well for them and that they could demonstrate a financial impact. There was a paper that came out this year, an economics paper, basically asking the question, does DNA testing reduce future crimes? And what they were looking at here was database expansions, plugging more stuff into the database. They're making an assumption here, or I guess they're finding their hypothesis, or their conclusion is that it reduces violent offenders by 17%, the number of future convictions, I should say, and property offenders. I'm not really sure if I know that, or if I believe they made a conclusion. One of their conclusions was that there's a deterrent effect. I don't really know about that because if you work in the lab and you start recognizing names, you kind of wonder about deterrence, and it's really bad when you start recognizing DNA profiles. Then you know that you've seen this person before. So, but if you do want to reduce future crime, one of the things that you want to do, obviously, is try to reduce the testing time, to speed it up. So that traditionally, there have been two methods generally used. Number one is hire more staff, so you get more people in to work more stuff. And number two is automate, right? You see automation all over the world. There's a lot of talk in the news about how automation is going to affect certain types of jobs. But basically, you're using humans for tasks that require intelligence. You use machines for repetitive processes. So just to show you the typical laboratory setup here, I'm not going to go through everything, but essentially what you can see in the middle of the screen is that everything from extraction through instrumental analysis has been automated for roughly 10 to 20 years, right? So these machines have been up and running. We just talked about that a little bit. Really, the two things that have been human required are, number one, identifying the material, right? That takes a brain to synthesize information, to kind of understand what I'm looking for, what kinds of tests are going to need to be run. And at the end, what's been typically human required is profile interpretation. That's not necessarily the case anymore, but I'm going to keep talking about human interpretation for a little bit. We talked about the plates here. This is an output plate, basically. Actually, it's a stack of output plates.
Something like this, right?
Yeah, exactly. That's a rack that you would hold up 96 tubes, or in this case, a plate containing 96 wells of sample. This is what you get when you're putting it on to the instrument for analysis. Typically, when you put it on this plate, you're going to have 6 to 8 allelic ladders, which are used for sizing. The computer uses these to identify the allele types. You have 2 PCR controls at least that tells you that your PCR test worked. Several DNA extraction blanks that tell you, are your extraction reagents contaminated? Not necessarily your sample, but the chemicals that you used to extract. And so a typical plate, if you're really, pumping it up, trying to be as efficient as possible, could have anywhere from 80 to 84 DNA profiles. So SWGDAM, Scientific Working Group on DNA Analysis Methods, came out with a new document this year for interpretation guidelines, which are applicable for human interpretation, and they make that point. It's roughly 90 pages long. If you're having trouble getting to sleep tonight, I would recommend you look it up. It'll knock you right out. But there's really one key guideline that I want to talk about. There's a lot of stuff in there, a lot of illustrations, a lot of things to look at for human interpretation, but here's the key guideline. To avoid confirmation bias, your evidence samples should be interpreted before comparison to knowns, right? So you look at your evidence, you figure out what your evidence is showing you, and then you look at your knowns afterwards. And confirmation bias, it's something that's been talked about for a while, and to basically, a short explanation of it is your brain wants things to make sense. You see things out there, your brain starts automatically looking for patterns. You try to identify things to make sense out of it because your brain doesn't really like disorder. So confirmation bias is basically where your brain has been preloaded with what someone or even you think you're supposed to see before you look at your actual evidence. So you're taking things in. You already have a preconceived notion of what you want to see, and it isn't necessarily, we think of bias as being something conscious, but this isn't necessarily conscious. It's completely unconscious, right? And so I want to give you an example. A famous case, you may have heard of it before, Dallas, Texas, November 22nd, 1963. Now, I should point out that this is purely coincidence that Trump released all this stuff last week. I already had it in my presentation, but it's just ended up being timely. But this is a photograph from across the street. So you can see here's the president right here. The famous film that you see is actually from the man. He's filming on this side. So this photograph is from across the street. It's a different view. That behind you, or behind here, that's the famous grassy knoll. And, well, if I think that there's another shooter in there, I start looking and, what's this, right? So I see a wall and I see something there. And now, here's something. This is this area that's circled, blown up, right? So keep in mind this is 1963. This is black and white film using grains. And Voila, there you go. There's your second gunman, right? So you can see here, there's a muzzle flash right there. Here's his badge. This is the famous badge man photo, right? The man who's dressed up as a police officer who's the real killer, right? There's his badge, the muzzle flash, the outline of his face. Also here, supposedly, here's a man in a T-shirt wearing a hard hat, right? And some mysterious man in a military uniform. But what's my point here? If you're looking at this, and without any knowledge, see, you can still see the guy there now, because I've already shown you what you're looking for. So your brain is automatically going to see that thing that I've given you after the fact. So if you're looking for a second gunman, well, there he is, right? It's confirmation bias. Well, maybe it's a real second gunman, but I'm not going to get into that. Anyway, so getting back, confirmation bias, so what I just said, you look at your evidence profile first, all your data. You infer the DNA types from the evidence without the knowledge of the known types, right? You compare your inferred types to your knowns, and then you determine if a match exists. And this is where, if you go back later on and look at any of the handouts, I have them electronically. I did not put them on my slide because or my presentation, because the ones I have, well, you saw how complex the ones that Greg had were, and mine are pretty rough. I have some simple ones that are real easy to interpret. I mean, anybody can figure them out. And then more of what we typically see in the lab, which are not easy at all. But going back to the plates, the 96 well plates, I ask myself, or you might ask, okay, we got an 8-hour workday, right? My public school math tells me that that's 480 minutes. Am I right? 8 times 6, 48? Yeah, I'm right. Yeah. Okay. 480 minutes divided by 84 DNA profiles allows you, in one workday, to spend 5 minutes and 42 seconds per DNA profile interpreting. Now, that's 5 minutes and 42 seconds. That means you're not taking phone calls, you're not checking your email, you're not going to the bathroom, you're not being bothered by your coworkers or something like that. You have 5 minutes and 42 seconds per profile on a full plate to figure out what's going on. And I submit to you these questions. Can a human interpret 48 samples in one workday? If they're all single source, which means DNA from one person, I'd say, yeah, probably. It depends on the complexity, right? If your DNA is of a low quality, you're going to have a little more trouble. But really, a single source profile is pretty simple to interpret. What about 2 people? Well, maybe. You're getting a little closer, and again, it depends on complexity. If you have DNA profiles that are in a mixture range of, say, 75 to 25% or 80 to 20, figuring out the major contributor there is pretty easy. The minor contributor is a lot more difficult. But I would tend to lean toward probably not on this. What about if you have mixtures from more than 2 people? Almost certainly not. You're not going to be able to figure that out in one day. And I talk about this for a reason, which I will get to later. But some of the complications then come about. Well, we talked about thresholds already, very, very briefly. Swigdam says you have to have them for a human being to interpret. The analytical threshold essentially is a number that you have identified per machine, by the way. It's not necessarily consistent from machine to machine, because each machine's a little bit different. So you can have a different threshold per machine that tells you that above this threshold, I accept that this is real data and not signal noise or background. Then you have a stochastic threshold, which is for this machine, and actually for this test kit, if you want to go even deeper, you could say for this color in the test kit, I have a stochastic threshold. Above this data, I will say that this is useful for using for interpretation and statistical methods. However, if you don't meet those thresholds, you can't use that data. So what you end up with was the volume of samples that that the lab has to test, the complexity of the samples, and when you throw in the thresholds, what you get is a lot of data declared inconclusive or too complex for interpretation. I know this because I've been doing this for 20 years. And this has been going on for quite a while. Too complex for interpretation. So basically, in doing this, you're potentially throwing away exculpatory information. You're potentially throwing away inculpatory information. You could have a sample in a case that points to the right person, but you're going to throw it away. And is that the only way you can do it? Well, Yoda says no. So what we do in our lab is we actually automate our interpretation using computers. So we take all of the information that we have. Again, going back to the philosophy, we use human beings for tasks that require intelligence and machines for repetitive processes. And we automate all of our interpretation with TrueAllele. I don't want to make this out to be a commercial for TrueAllele. It's a system we use, but we love it because of what it can do. Also, I don't know if you've ever seen, you may have seen this slide before. I know the guys from Cybernetics have seen this slide before because I ripped it off from one of their presentations. But I always consider plagiarism to be the sincerest form of flattery. So this is basically you have a desktop computer, you have a database server where you send everything up. The server interprets the data, processes everything, and then you pull it back from the server and you compare all your results. So our process is basically we take that entire plate of data, right, everything that we have run, and upload the entire plate to the server. Okay? The computer interprets the mixtures. We walk away and do other work while the computer is working. After the computer's done, we check the results. We pull them back from the computer. We tell the computer, compare all of the evidence profiles to each other. So we're looking for matches within the evidence, within the case, from case to case. We compare it to known profiles, right, within that case. On the entire plate, we compare it to that. And to previous runs, things that we have stored already in our database. So all of our historical data, we can go back and look at this plate and say, do we have anything here that potentially matches? So these are the benefits. Did I skip something? Detailed processing. Yeah, so if we see something that looks like a potential match, we pull that one, and then we go back and do a lot more detailed work on it. We look at it more in depth. We may have to change some of our assumptions, and then we look for, I already talked about it this morning, concordance among runs. We'll do 2-3 runs and look for concordance there, make sure that we're getting the right result, or a result that is reproducible. So here's the benefits that we use, right? So immediately, everything's looked at. We don't throw anything out. We look at everything on that plate, every sample in that run, every sample in that batch. The speed. So all of these too complex for interpretation samples, our computer will do them in about 6 hours. So where a person could not do it in a day, in a workday, we do it in less than a workday. Actually, we don't. Our computer does in less than a workday. This is a really key thing. There's no confirmation bias here. The computer looks at everything. The computer doesn't have any prior knowledge of what it's supposed to see. It doesn't have any prior knowledge of a suspect, a victim, an elimination sample, nothing. It looks at all the data, it pulls the genotypes out, and then it compares it afterwards when it's already done. We restore human work time, right? So we can go back and do other things while the computer's still solving. It assists with CODIS entry. So sometimes in these complex mixtures, as a person, you're not really sure if there's something there that you can upload to the national database. But with the use of the computer, it can identify alleles that are more probable than others. And also assessing candidate matches. So when we put these more complex mixtures in, sometimes we will get matches to multiple offenders. I should say not real matches, candidate matches. And what the computer can do, since we've already run it, we can then compare to those offender profiles that come back and say, no match, no match, no match, no match, because the work is already done. I should actually point out that we had one like this that The CODIS software told us to expect one match or less in the national database. We got 3 matches back to 3 different offenders in 3 different states. One of them, human interpretation probably could eliminate. 2 of them, human interpretation could not eliminate. The CPI, incidentally, the human match score would have been 1 in 10 billion on that. With TrueAllele assisting us there, one guy had a likelihood ratio of about 2, and the other one was, I think, in the tens of billions, I believe. So we could, using the computer, eliminate one person immediately, whereas using the human interpretation, you have one guy that's wrongfully matched to a sample. Now, in reality, further investigation would have probably cleared that guy, probably, but you can't say for certain. But at what cost and time of having to go through all that investigative work when we had it done in 5 minutes using work that we'd already done. Also, automation, we can compare all of our evidence profiles that we have run in this batch to all known samples in the batch. So when you're talking about a plate, potentially a plate setup, incidentally, we don't do that for sample setup.
You don't do by hand?
No, we do direct amp on our knowns, so they're never on the same plate. I just want to point that out.
Right, no, I appreciate it. You listened.
So we look at everything that's on that entire plate and compare it to everything else. This is one of the things that I talked to Dr. Perlin about the first time I met him. One of my interests in using TrueAllele was for quality control, right? For comparison of all this data to lab staff and crime scene officers, because a lot of labs do put staff members into CODIS. However, a database can only compare the things that are in the database. So if you have a sample that's not in that database, it's never going to get compared to your lab staff. So one of the things I wanted to do was say, okay, well, if we use TrueAllele in this automated fashion, then we can compare everything to all of our guys in the lab all the time. So our goal here is identifying more case-to-case matches, but also potential contamination. And I want to talk about just a matching thing, a pretty interesting matching data that, I got it, so we went up and uploaded historically all of our data from about 7 years of testing, 7,500 DNA profiles, 20,000 inferred genotypes, basically. And I asked, how many matches do we have? So around 30,000 potential matches came back on an Excel spreadsheet. Most of these were within case, right? So case 1, sample A matching to sample B, matching to sample C, which you kind of expect to see. But interestingly, just a real cursory perusal of the data shows me 5 samples from 5 different cases that match to each other and nothing else in the database. So I thought, oh, this is interesting. So here's our list of cases. You'll note that they're from different years, different type of crimes. The one that really sticks out, well, the 2 things that really stick out, number 1, you have known suspects in most of these cases. You know, in only one case, you have an unknown suspect. The other one is the car break-in, right? I mean, you can kind of see a home invasion, an attempted murder, and a murder. And there's kind of, you can maybe see that same person potentially. But a car break-in, and then with 3 known suspects. None of the named suspects were the same. The 2015 attempted murder and the 2016 murder, the identity was not in dispute. It was the circumstances that were in dispute. And then in the car break-in, the suspects were witnessed actually doing this and caught soon after. So, what do we have? Wrongfully accused? Is there a mystery, person that we don't know about? Maybe the Phantom of Heilbronn came to America, or contamination. So, my first thought in the lab is, what did we do wrong in the lab, right? So, they worked in the lab at different times. None of the cases were actually in the lab at the same time. 3 different people worked the cases. So that's not it. Just to make certain, I went back and manually, well, not manually by myself, in TrueAllele, I pulled these genotypes and pulled the lab staff samples in, and they didn't match. Did not match any case reference samples. They're all worked by the same agency. They're all touch DNA. That's an important thing. I want you to keep that as a take-home message, by the way. all evidence was collected or handled by the same investigator who was the only common link between all 5 cases, which led to this reaction in the lab, right? I'm looking for images, and there's Kirk and Picard, and I thought, I could use Picard, but he's just too French. So I went with Kirk. Anyway, so yeah, we ended up getting a buckle standard from this investigator, and not surprisingly, he does match. Incidentally, it was kind of funny getting that out of him. I asked him, hey, we think we got some matches here. They're probably you. Will you give us a buckle standard? Why do you need that? Well, I just told you. And so finally, my response was, hey, look, man, it's probably you. One of these profiles is in the state database system. One of these profiles is in the national DNA system. If you're comfortable with your profile being in a criminal database, knock yourself out. And the next day, the sample was submitted. So, but we have other potential contamination events under investigation. Incidentally, they're all on touch DNA items. And most of these would not have been identified in CODIS either because they didn't qualify for entry or they were too complex to be searched with a manual keyboard search against our staff profile. So the questions I have for us is this unusual or typical? How many are being contaminated across the country before they ever come to the lab, right? Because in the lab, we generally have pretty good standards. We're gowned up, we're masked, we bleach our gloves before we handle the evidence. We change our gloves between evidence, but is your crime scene investigator doing that? Probably not. And do labs have the ability even to detect this? This is multiple cases over multiple years. We didn't know it because we couldn't see it. So, areas that, we need to improve on: better evidence handling and collection, particularly at the scene, better understanding of DNA transfer. How does touch DNA get transferred from one object to another? Because just because you find somebody's DNA on an item doesn't mean he handled that piece. It could have been transferred from some other person to that piece of evidence. Interpret all the mixture data and search everything against all officers. So here's a hypothetical scenario. You get some drug packaging submitted to the lab. Suspect's DNA is on the packaging. The officer's DNA is also on the packaging. What's the conclusion there? So Saul Goodman says his client was framed. I just wanted to find a way to shoehorn in Saul Goodman here. But contamination kind of went away as a defense argument years ago when you're dealing with body fluids, blood, semen, saliva. But when you start talking about touch DNA, it's going to be coming back in just because of the way that touch DNA can be transferred. So my summary here, you can automate interpretation. You can do it without bias. Looks at it without bias. You can compare everything to all references. It improves your quality control and frees your staff up for other tasks. So with that, I won't take any questions because Mark says I have to go.